My name is Travis Johnston, and for the next few minutes, I'm going to share with you the work that I did for the Automated Discovery and Analysis of Temperature-Dependent Structural Changes data challenge. The overall goal of this challenge is to identify a temperature at which a structural change occurs. The data I was provided is neutron powder diffraction data, which consists of 140 intensity curves. Each intensity curve corresponds to the temperature of the material. It's convenient to think about each intensity curve as either an n-dimensional vector, and n is fairly large here, it's about 6,000, or as a point in n-dimensional space. And since it's hard to visualize data in 6,000 dimensions, give or take, I began by using multidimensional scaling to reduce the data down to 2 dimensions. Multidimensional scaling works by taking a distance matrix, in this case a 140 by 140 distance matrix, and then finding a set of points in 2D whose pairwise distances match those in the distance matrix as closely as possible. Multidimensional scaling allows us to reduce the dimensionality of the data while preserving the meaningful distances. Next, I clustered the data using an algorithm called DBSCAN. DBSCAN works by grouping areas of high point density as clusters. Points that are not in the regions of high density are considered noise. The user need only specify what dense means in context. DBSCAN has several advantages. So in this case, it's most beneficial because it doesn't make any assumptions about the shape of a cluster, and it allows for points to remain unclustered. The figure on the left shows the result of using multidimensional scaling and DBSCAN on the data provided. DBSCAN generated 2 clusters. The first cluster, indicated with green circles, happened to contain all the intensity curves whose temperature was under 134 degrees. I'll call this the cool cluster. The second cluster, indicated with orange triangles, happened to contain all the intensity curves whose temperature was above 173 degrees. This I'm going to call the warm cluster. In between are these small black dots which were not clustered. DBSCAN considered these points noise, and I'll consider them as transition temperatures. For the remaining few slides, I'll endeavor to convince you that these conclusions are correct. Specifically, that there are 2 steady states before about 134 degrees and after about 173 degrees. And in between 134 and 173 degrees, a structural transition occurs. I'll now demonstrate how effective the clustering was by showing the intensity curve for each temperature and identifying peaks. As the temperature starts to increase, pay attention to the darkest peak and its center. We'll observe the peak shrink, split into a triple peak actually, and then it will recombine as it all moves slightly to the right. So here the temperatures are increasing, and we're all in the cool region now. The color corresponds to the cluster that we're in. As we start to get closer to that 134, you'll notice the smaller peaks in the middle start to shrink. That'll start happening here. As those peaks shrink, we broadened out, we became a triple peak, and now it's recombining. It's a split peak and then back to a single peak. And as we watch, we can see the center of that is drifting to the right. You can see it slowly ticking up there as we move on. And this continues all the way out to about 300 degrees where the temperature stops. Okay, finally, I'll briefly show you the width, area, and center of the darkest peak as a function of temperature. In this figure, we see that the peak of interest is much wider during the transitioning temperatures, 134 to 173 degrees. This clearly indicates that something is different here. Likewise, the total area of the peak of interest is larger during the same temperature window. We can also see in this figure that the typical area of the peak in the cooler temperature range is smaller than the typical area in the warmer temperature range. And finally, during the animation, we observed that the peak of interest was drifting to the right. We also observed this in this figure. If we look close enough, we can even see that the rate at which the peak drifts to the right, that's the slope of the line in this case, is higher in the warmer temperature region than in the cooler temperature region, and it's moving the most during that transition phase. And all these clues together lead us to conclude that the technique of multidimensional scaling combined with clustering using DBSCAN effectively captured the transition that we were seeking.